We live in a world that's, well, increasingly shaped by algorithms, by AI, and now machines are even starting to generate mathematical proofs.
Yeah, it's really quite something. We're seeing AI assist with complex theorems, even suggest new conjectures.
Exactly. And it throws this really old question into sharp focus, doesn't it? Are these machines inventing something new, mathematically speaking, or are they just, discovering truths that were already there, just much faster than we ever could?
It's a huge question. It goes right to the heart of how we understand knowledge, reality itself, maybe even consciousness.
Welcome to the Urban Herald. Today our team is taking you on a deep dive into one of philosophy's, well, greatest debates. When a mathematician presents a new theorem, is it like they've charted an unknown island? Or more like they've designed a completely new building?
Invention versus discovery. That's the core tension.
And we're going to unpack this. We'll look at the arguments on both sides and help you figure out what this all means for how you see scientific truth, maybe even the fabric of reality. So, okay, let's get right into it. At its heart, what's the philosophy of mathematics really wrestling with here?
Well, it's wrestling with this fundamental question. Do mathematical things, numbers, shapes, logic, do they exist out there somewhere independent of us, or are they basically intricate constructions of our own minds?
Right. Does three exist whether humans are here or not?
Exactly. And this isn't just, some abstract academic game. It directly impacts how we think about mathematical truth. What does it mean for something to be true in math? And how does that relate to the physical world we experience?
Okay, so give us an example maybe.
Think about proving there's an infinite number of prime numbers. It's a classic proof. Is the person doing that proof pulling back a sort of curtain on an eternal truth that was always there?
The discovery view.
Or are they carefully, logically building an argument, an edifice within a system that humans created?
The invention view.
Precisely. And the implications of which one you lean towards, well, they're pretty vast.
That sets things up perfectly. So let's start with the invention side. The idea that mathematics is fundamentally a human creation. What's the evidence for that? What makes us think we invented math?
Well, there's quite a bit, actually. One really strong line of argument comes from looking at how mathematical frameworks themselves are built.
Hmm.
They often start from human choices, from basic assumptions we decide on. We call these axiomatic systems.
Okay, like geometry starting with Euclid's postulates, those basic assumptions.
Exactly like Euclid. But then fast forward to the 19th century, you get this revolution with non-Euclidean geometries. People like Gauss, Bolyai, Lobachevsky, they didn't just accidentally find new types of space.
What do they do?
They consciously changed one of Euclid's fundamental assumptions, the parallel postulate, and by doing that, they created entirely new, perfectly consistent systems of geometry.
So geometries that work differently but are still logically sound?
Yes. And these different geometries are useful for different things. Euclidean works great for flat surfaces, right? But these other ones are crucial for things like Einstein's theory of relativity describing curved spacetime.
Ah, so the fact that we can create different useful systems by changing the basic rules suggests we're inventing tools, not just finding one map.
That's a great way to put it. It really highlights mathematics as this incredibly sophisticated, adaptable toolkit that humans have crafted.
Okay, that makes sense. The choice involved in axioms.
Yeah.
What about how math developed across different cultures? Does that point to invention too?
Oh, absolutely. I mean, if math was just out there waiting to be discovered in one single form, you might expect everyone to find the same things in roughly the same way. But that's not really what we see.
What do we see instead?
We see incredible diversity and innovation across cultures. Look at number systems. The Babylonians used a base 60 system. We still see echoes of that in our timekeeping, right? 60 seconds, 60 minutes.
Yeah.
Mayan mathematicians, completely independently, developed a really advanced base 20 system. And they had a sophisticated concept of zero, way ahead of many others.
And elsewhere.
Chinese mathematicians used rod numerals, a totally different approach. And today, well, computers run on binary, base 2. It looks much more like different groups inventing systems that worked for them.
You mentioned zero there. That feels like a really big one. Was zero invented?
It seems very much like an invention, yes. Zero is kind of a showcase for this idea. Indian mathematicians like Brahmagupta around the 7th century really formalized the concept and its rules.
But not everyone had it before then.
No. Greek mathematics, for all its incredible achievements, basically operated without a concept of zero as a number in its own right. They had ways to talk about nothingness, but not zero in the way we use it, as a placeholder or a number you can calculate with.
Huh. So if math truths were just universal things to be discovered.
You'd kind of think zero would be obvious to everyone from the start, wouldn't you? Instead, you see it being developed, refined, spreading across cultures. That looks a lot like how other major human inventions progressed.
And it's not just the big concepts, is it? What do I just... The way math looks. The symbols.
You're right. That's maybe the most obvious evidence for invention. Mathematical notation, the symbols we use every day, like plus only, the numerals 1, 2, 3, the symbols in algebra, calculus symbols like A for integration. These are undeniable human creations.
They didn't just appear out of thin air.
Not at all. They evolved over centuries. People were constantly tinkering, trying to find clearer, more efficient ways to write things down. Think about algebra. It started out written entirely in words rhetorical algebra.
Like, the thing plus 2 times the thing equals 5.
Exactly like that. Very wordy. Then it moved through stages to become the symbolic algebra we use today with X's and Y's. That whole journey is about humans inventing better tools for expressing mathematical ideas.
So even the way we prove things in math, could that have cultural fingerprints?
It seems so. While we often think of proof as this purely objective thing, the style and methods of proof have varied. The ancient Greeks, think Euclid again, really emphasized visual geometric proofs.
Lots of diagrams.
Definitely. Arabic mathematicians were pioneers in using algebraic methods for proofs. Chinese mathematical traditions often involved algorithmic approaches, step-by-step procedures. Indian mathematicians developed very sophisticated numerical techniques.
So different paths to demonstrating truth.
Different paths, different styles, different toolkits being emphasized. It suggests that even the rigorous process of proof isn't totally separate from the culture that develops it. It adds weight to the idea that we're building these structures.
Okay, that's a really strong case for mathematics as a human invention. A brilliant, evolving craft. But then there's the other side. The argument that math is actually discovered, that it's already out there, waiting. And this is where it gets, well, kind of mind-bending.
It really does, because despite all that evidence for invention, there are some aspects of mathematics that just feel incredibly discovered. Its power, its consistency, the way it seems woven into the fabric of the universe. It leads many people, philosophers and mathematicians alike, to think we're uncovering something profound.
This is the Platonist idea, right?
It's the classic term for it, yes. Mathematical Platonism, going back to Plato himself. The idea is that mathematical objects, numbers, perfect circles, the relationships between them exist in some kind of abstract realm, independent of human minds, independent of the physical world.
So they're real, just not physical.
Exactly. And mathematicians in this view are more like explorers. They're discovering the features of this already existing realm, mapping it out. They aren't inventing the theorems, they're finding them.
Like finding a continent that was always there, you just needed the right ship to reach it.
Yeah.
Is there evidence for this kind of consistency? Finding the same continent from different places?
There is, and it's quite compelling. Think about the Pythagorean theorem, A plus B or EC for right-angled triangles.
Yeah, everyone learns that one.
Well, the remarkable thing is that variations or specific cases of this relationship were discovered independently by ancient mathematicians in Greece, yes, but also in India, China, maybe even Babylon. They were working in different systems, different notations, different times.
But they found the same fundamental relationship about triangles.
Exactly. It strongly suggests they weren't just inventing separate ideas that happened to look similar. It feels like they stumbled upon the same underlying eternal truth. This universality is a cornerstone of the discovery argument.
Okay, beyond geometry, are there other universal constants or relationships that pop up everywhere?
Oh, absolutely. There are these fundamental numbers and relationships that seem constant across all cultures, all of history, and even appear in nature itself. Pi is a great example.
The ratio of a circle's circumference to its diameter.
Always the same value, approximately 3.14159, no matter who is measuring or when. Prime numbers 2, 3, 5, 7, 11, and so on. That sequence is the same everywhere. The golden ratio, Fu-Fi, roughly 1.618. It shows up in art, architecture, and strangely often in nature.
And the Fibonacci sequence. That one always feels particularly spooky in how it appears in the natural world.
It really does, doesn't it? The sequence 1, 1, 2, 3, 5, 8, 13, where you add the last two numbers to get the next one, You see this pattern dictating the arrangement of seeds in a sunflower head, the spirals on a pine cone.
The chambers in a nautilus shell.
Yes, even the spiral arms of galaxies sometimes approximate it. It's hard to look at that kind of pervasive pattern and think humans just invented it. It feels much more like we're observing and discovering some underlying mathematical rule of the universe.
Which leads perfectly into this idea of the unreasonable effectiveness of mathematics, right?
Yeah.
I think it was the physicist Eugene Wigner who coined that phrase.
That's right, Wigner. And it's a really powerful point for the discovery side. How can it be that mathematical ideas, often developed with absolutely no practical application in mind, just pursued for their own internal logic or beauty, turn out later to be incredibly, almost uncannily effective at describing the physical world?
It would be a massive coincidence if we just made it all up, and it happened to fit reality so well.
It seems that way. If math is just a game we invented, why does it correspond so perfectly to reality? It feels almost mysterious.
What are some examples of this? Math developed for its own sake that later became essential for physics.
There are many. Complex numbers involving the square root of -1 were initially seen as just a mathematical curiosity, almost imaginary, hence the name.
Right, imaginary numbers.
But now,
Hmm.
they're absolutely essential for the mathematics of quantum mechanics, our fundamental theory of the very small, or think back to those non-Euclidean geometries we talked about.
Developed by changing axioms.
Yes, as abstract systems. But then Einstein realized one type of non-Euclidean geometry was precisely what he needed to describe gravity in his theory of general relativity, or group theory, a very abstract branch of algebra, it turns out, to perfectly describe symmetries in particle physics.
It's like the universe already speaks that language.
It really feels that way sometimes. Even simple things, like hexagons. Why do bees build hexagonal honeycombs? Why do snowflakes often have hexagonal symmetry? Why do some basalt columns form hexagonal shapes?
Yes, that's it, right.
Incredibly efficient for tiling a surface or packing things tightly. Bees didn't, take a geometry class. It seems they, or rather evolution, discovered that this mathematical shape provides the best solution.
That's a fantastic example. It does make you think. What about when different mathematicians, working totally separately, discover the same thing around the same time? Does that happen?
It happens surprisingly often, and it's another strong argument for discovery. If mathematical truths are just out there waiting to be found, it makes sense that different explorers, if they're looking in the right area, might find the same thing independently.
Like,
The most famous example is probably the development of calculus. Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany both developed the fundamental ideas of calculus independently in the late 17th century.
and the non-Euclidean geometry guys.
Them too. Gauss, Bolyai, Lobachevsky. They all arrived at hyperbolic geometry independently around the same time. There are many other examples in complex analysis, statistical mechanics. If math were purely invention, like writing different novels, you wouldn't expect such identical plots to emerge simultaneously.
It suggests they're all describing the same underlying reality.
That's the inference, yes. It points towards a pre-existing landscape of mathematical truth that they are tapping into.
And what about the act of proof itself? When a mathematician proves a theorem, does that feel more like invention or discovery?
The nature of mathematical proof often feels very much like discovery. A proof uses rigorous logical deduction. It doesn't seem to create the truth. It reveals why something must be true, given the starting assumptions.
It's uncovering a necessary connection.
Exactly. It feels like uncovering these inevitable logical consequences. And often there's this sense of beauty and elegance in mathematical proofs, a feeling that you're glimpsing something objective and profound. Think about Euler's identity. A sup plus 1 equals 0.
That connects 5 of the most fundamental constants in mathematics, right? E, I, pi, 1, and 0.
Yes. In this incredibly simple, unexpected equation, many mathematicians find it breathtakingly beautiful. It feels so profound, so perfect. It's hard to imagine it's just a coincidence of human invention. It seems to hint at some deeper, inherent mathematical reality we've uncovered.
Okay, wow. So we have these really compelling arguments on both sides. Invention, driven by human choice, culture, notation, and discovery, suggested by universality, effectiveness, simultaneous findings. Is it possible the answer isn't strictly one or the other? Could it be?
Both. That's definitely where a lot of modern thinking is heading. This idea that maybe the invention versus discovery framing is a bit of a false dichotomy. Perhaps mathematics isn't either invented or discovered, but involves a complex interplay of both.
How would that work? Both invention and discovery.
Well, think of it like this. Humans invent the languages of mathematics, the symbols, the rules of the game, the axiomatic systems. That's our creative input. But then within those invented systems, we discover truths and relationships that are necessary consequences of those rules. Truths that were, in a sense, implicitly there all along.
Ah, like inventing the rules of chess.
That's a fantastic analogy. We invent the board, the pieces, how they move. That's the human creation. But once those rules are set, the infinite number of possible games, the best strategies, the checkmate patterns, those are all things we discover within the system we created. They weren't individually invented, they were consequences waiting to be found.
That makes a lot of sense. So we invent the framework, but discover what's possible inside it. Is there another way to think about it, maybe like language?
Yes, the language analogy is quite useful too. Linguists find evidence for universal grammatical structures, sort of deep patterns common to all human languages. That suggests some element of discovery about our own cognitive architecture.
But obviously French and Japanese and Swahili are different inventions.
Exactly. While the underlying capacity or structure might be universal discovery, the specific languages with their unique vocabularies and grammatical quirks are human inventions. Maybe math is similar. There are universal relationships and structures out there in reality, discovery, but we invent specific symbolic systems and formalisms to capture and express them. Invention.
Okay, so where do our own minds, our brains, fit into this picture? Do we have some kind of innate mathematical sense that bridges this gap?
That's another fascinating part of the puzzle. There's growing evidence that humans, and maybe even some animals, do have some basic innate mathematical intuition,
Like what?
a rudimentary number sense, the ability to estimate quantities, numerosity, an intuitive grasp of basic geometry in space, a powerful drive to recognize patterns. These seem quite fundamental, perhaps hardwired.
So our brains are kind of pre-adapted to resonate with the mathematical structures in the universe.
That could be part of it. It might explain why mathematics feels both natural to us and also so effective in describing reality. Our cognitive architecture might have evolved in a universe that is inherently mathematical, leading to this alignment.
Any examples of this intuition in action?
Well, the story of Srinivasa Ramanujan is quite extraordinary. The Indian mathematician who produced incredible, complex theorems, often saying they came to him as insights or visions, with little formal proof initially.
And leader mathematicians proved them rigorously.
Many of them, yes. It's as if his intuition was deeply connected to this underlying mathematical reality, even if he didn't always follow the conventional steps of invention or proof. It suggests human consciousness might have a more direct line to mathematical truth than we sometimes assume.
This is really profound stuff. And it's not just abstract philosophy, is it? This whole debate must have real-world consequences for how we teach math, how we do research. So for you listening, what does this actually mean in practice?
It definitely influences how we might approach mathematics education. If you lean heavily towards discovery, you might emphasize exploration, letting students find patterns, fostering that sense of wonder about pre-existing truths.
Like being a nature guide in the mathematical world.
Kind of, yes. Whereas if you focus on invention, you might put more emphasis on mastering the formal systems, understanding logical construction, appreciating the power of the tools humans have built.
Building the mathematical structures.
Right. And a synthetic view, acknowledging both, would suggest we need to cultivate both aspects. The ability to explore and discover, and the skills to rigorously define, construct, and apply mathematical systems.
And what about research? Does it change what mathematicians prioritize?
It can. Someone driven by the discovery view might be guided more by aesthetics, seeking beauty and elegance as signs they're on the path to fundamental truth. A researcher leaning towards invention might prioritize creating new mathematical tools to solve specific problems, focusing more on utility.
But ideally, maybe both.
Ideally, yes. The synthetic approach encourages pursuing both seeking deep, beautiful truths and developing powerful, practical tools. They often go hand in hand, actually.
And let's loop back to where we started AI. How does the rise of AI mathematicians fit into this synthesis now?
It adds a whole new layer, doesn't it? When an AI system proves a theorem humans couldn't, or finds a pattern we missed, what's happening? Is it just demonstrating the power of complex systems we invented, the algorithms, the hardware?
The invention perspective on AI's work.
Or is the AI acting as a new kind of explorer, accessing that same platonic realm of mathematical truth, perhaps more efficiently than us? Does it point towards truth being independent of the type of mind, human or artificial?
The discovery perspective, it really blurs the lines.
It certainly does, and new areas of mathematics itself, like category theory, are emerging. They focus on relationships and structures in a very abstract way, and some think these new frameworks might offer ways to sort of formally bridge this gap between invention and discovery.
So the debate isn't settled, but maybe we're finding more nuanced ways to think about it.
Exactly. The very persistence of this debate tells us something important. It touches on these fundamental questions about knowledge, reality, and our own minds.
Wow. What an incredible journey through, well, one of the deepest questions we can ask. We've explored some really powerful arguments on both sides. And I think it's clear that whether you see math primarily as an invention or a discovery, its ability to describe and illuminate the universe is just undeniable.
Absolutely. And that synthesis view is really compelling, isn't it? The idea that we simultaneously invent the languages and frameworks while discovering the truths and patterns embedded within them and perhaps within reality itself. We create the tools, but uncover the universe's secrets.
From the sheer elegance of something like Euler's identity, connecting those fundamental constants to the intricate spirals in a sunflower head. Mathematics really stands as our most powerful language for understanding reality, and maybe one of our most refined expressions of rational thought.
And when you contemplate this question, invention or discovery, you're doing more than just philosophy of math. You're really thinking about how mind meets reality, how our finite consciousness can somehow grasp these seemingly infinite, eternal truths.
You know, how human creativity interacts with what seems like a universal, elegant structure underlying everything.
Mhm.
And perhaps, just engaging with that mystery. Maybe that's part of what it means to be human. Thank you for joining our team here at the Urban Herald for this deep dive. Keep exploring, keep asking questions, and keep an eye out for all the mathematical wonders hiding in plain sight all around you.